So using electrochemical cells and electrode potentials, etc., especially when you're first introduced to it, can feel quite daunting. I know it can. Again, as with a lot of A-level chemistry, I think personally that this is one of the topics where if you understand it, there's a lot less to learn. If you can understand what's going on, you can apply that understanding to every question you've been given. Getting to the point where you can understand it, though, is extremely difficult. I do know that. So I'll do my best to explain things. But if you still struggle with questions on electrochemical cells, I would highly recommend you get yourself to the point where you can understand what is happening. So, watch YouTube videos, read through different revision guides, etc. Try to wrap your head around what is happening. And if that involves drawing pictures or creating diagrams to help understand it, then please do that. I know, because this is such an abstract concept, that this idea of a redox potential, for example, is such an abstract concept. It's really difficult to get your head around what it means. So come up with models for it, or find people that have created models for it and use those. But yes, let's see what we're going to look at here. So we'll think about electrochemical cells. We're going to look at half cells, how they're created, how we denote them, all that sort of thing. We're going to look at some standard electrode potentials and any calculations that are associated with it, and the electrochemical series and calculations associated with that. We're also then going to think very briefly, and I wish you could you could easily spend a day just looking at applications of electrochemical cells. For example, the hydrogen-oxygen fuel cell, because again, it's another layer or another level of complexity within hydrogen-oxygen fuel cells. So it's just not easy. So we will try and cover the main bits, the main concepts. I will also point out, though, hydrogen-oxygen fuel cells and how much detail they go into is very different across exam boards. So again, make sure you're confident with your specification. Read through. Are you expected to know it in acidic conditions and or alkaline conditions? Are you expected to know overall equations or individual equations, etc.? But I'll come to that again when we approach it, when we come across it. So electrochemical cells, again, spec points for you. If you're an Edexcel student, it is these spec points we're going to be covering. And if you're AQA or OCR, then these are the ones we're going to be looking at. So electrochemical cells, this is one of the topics where I'm very fussy with how I teach it. So I apologize if this is different to how you've been taught it. I know that, different people will understand it in different ways, and different people will think about things in different ways. But I like to teach it in terms of reduction potentials. So I'll explain what that means in a second. But half cells, funnily enough, two half cells combine to form one electrochemical cell, because they're a half cell. Each half cell contains an element in two oxidation states and an electrode that conducts electricity. Sometimes one of the elements, the element in one of its oxidation states can be its own electrode, and that's absolutely fine. So metals, solid metals that also become ionic or aqueous metals, sorry, my brain went funny then. Solid metals can often be their own electrode because they are a solid, they're metal, so they can be an electrode that can conduct electricity and provide a surface for the reaction between the aqueous substance and the solid metal itself. Obviously, and we'll come to it again later, if one of the oxidation states is not solid and or is not just a normal metal, then we will need to provide an electrode. And we'll come to that again in a second. In each half cell, both reduction and oxidation can occur, setting up an equilibrium. Which half cell does what in... So I think that's written slightly funnily. It should be in the electrochemical cell, both reduction and oxidation occur. One half cell is oxidation, one half cell is reduction, is what it's trying to say. Which half cell does what in the cell depends on their standard... where am I going to write that? No, sorry. Standard, there we go. Standard, crikey. Standard electrode reduction, and I'm going to put reduction in brackets because this is the bit where I'm fussy. I like to call them reduction potentials because that's what it is. They're not often taught like that. They're often just taught as standard electrode potentials. So I'm going to use the term standard electrode reduction potentials, or just reduction potentials. Potentials E thingy with the standard symbol again. It's the same symbol. We're just calling it an an electrode. Standard electrode reduction potential. The reason that I like to call them a reduction potential is because I think it helps us to understand what's happening and when and why reactions can and can't happen. If we just remind ourselves of oil rig, we cover it at GCSE, we still use it at A level, it's still applicable. Oil rig is oxidation. Oh my goodness, my spelling. Oxidation is loss, reduction is gain of electrons. It's the same as it was at GCSE. Oil rig is applicable for electrons, the exchange of electrons. So oxidation is the loss of electrons, reduction is gain. And this red box, I personally have never learnt what an oxidizing agent does or can do, or a reducing agent does or can do, because I work it out every time. So you can learn it off by heart if you want, or you can understand it and then work it out. So oxidizing agents, if it's an oxidizing agent, then it is going to be oxidizing something. So if it's oxidizing something, then oxidation is loss, so it's causing something to lose electrons. So the way it can do that is by it gaining those electrons, forcing something to lose electrons. So it is gaining electrons, so it is reduced. Reduction is gain of electrons. I know it's a long way around and you might prefer to just memorize it, but by doing that, I've leaved space in my brain to memorize something else. And similar for reducing agent. A reducing agent is going to reduce something else. It reduces something else. It causes something else to gain electrons by losing electrons and giving that thing electrons. So it itself is oxidized. Okay, so let's have a look then at a full cell which includes zinc and copper half cells. So this is a kind of an example. Obviously, you guys wouldn't use color, but this is an example of a diagram you may be asked to draw for a cell. And you do need to be able to label it correctly. So here we've got, what do we say, zinc and copper. So we haven't been given information either way, but I will tell you now, copper is reduction. The copper half cell undergoes reduction, zinc undergoes oxidation. So which way around do you write it? Which usually, not all the time, because the standard hydrogen electrode makes things a little bit more awkward, but which way around do we usually write things? And I can promise you there is a way. We write reduction on the right when we're doing standard notation, when we're doing diagrams, when we're, I'm sure there's not somewhere else. Anyway, reduction on the right. So this right-hand side is reduction, or shows reduction. That is the reduction half cell. And so the left-hand side must be oxidation. Reduction on the right. Oh my goodness, my handwriting. Reduction on the right. That's redden, reduction on the right. What did I say? Copper is reduction. So this is copper. So what's going to be what? Where is copper going to exist? That must be copper solid. That's my electrode. Actually, let's call it a copper electrode. That makes more sense. Electrode. And therefore, I'm going to have copper in solution, an aqueous solution of copper. Which ion is it likely to be? It's most likely to be copper 2+. Solution. And therefore, on the right, this must be my zinc electrode. Oops, he's treading on something. Zinc electrode. And this must be my zinc solution. Oh, I didn't give it a charge, sorry. And again, it would be Zn2+, so zinc 2+ solution. What else can I label on this diagram? You don't need to label beakers or wires, but what's this thing likely to be, or what does it look like it could be? It's going to be a voltmeter, useful for measuring the electromotive force, the EMF of the cell as a whole. And then this thing in the middle is what? That is our salt bridge. Make sure I spelled that right. What else did I want to include? Oh, I'll just put Zn2+ aqueous there, just to make it absolutely clear, and copper 2+ aqueous. So that is a copper solution. Oh, equations, that's a good idea. So what equations are going to happen? And I'm going to write them as the reduction equation, because your reduction potentials are given as the reduction equation. So reduction, oil rig, reduction is gain of electrons. So I can show my zinc, Zn2+, gaining 2 electrons in a reversible reaction to form Zn solid. And my copper, I can use copper 2+ aqueous, gaining 2 electrons to become copper solid. That is reduction in both cases, but we have already said reduction goes on the right, so that will be traveling, the equilibrium will be pushed way over to the right on that equation. So we will be mainly going in the forwards direction. But with the zinc equation, that is going to be pushed in the backwards direction. So you'll actually be getting oxidation happening. And that is, we can label those as oxidation therefore and reduction. Was there anything else I wanted to say? Can't remember. Let's add that down there. So note the more negative electropotential is drawn on the left, or I would think about it in terms of reduction. So reduction is on the right. So the more positive reduction potential, the more likely thing to be reduced. The more positive reduction potential goes on the right. Reduction on the right. RR. Bit easier to remember, I think. And again, I would personally think about it in terms of reduction, because that's what our reduction potentials are given as reduction. Okay, what else? Oh, and I'll just put, there should be a usually in there, because of course within the standard hydrogen electrode, when we're measuring electrochemical, we're measuring the electropotential of specific half cells. The standard hydrogen electrode is always on the left, so sometimes you won't have the more negative electrode potential on the left. Sometimes it will be on the right. So usually we draw reduction on the right, apart from maybe with the standard hydrogen electrode. Okay, let's keep going. Why do we have a salt bridge? What's the point of a salt bridge? Salt bridges are used to allow ions to move around the circuit, but preventing the solutions using individual half cells to mix, or from mixing. Preventing them from mixing. We know that in order to have a successful circuit, it must be a complete circuit. Now you could have 2 beakers and stick the electrodes in with a voltmeter, and you would see a current flowing for a while, but eventually you would lose the potential, would lose the momentum of the electrochemical cell, because you would end up losing concentration on one side, gaining concentration on the other. You'd end up building up too much. I don't want to use the word pressure, that's the wrong word, but you would lose the voltage behind the cell, so it wouldn't work forever, or it would stop working quite quickly. If you have a salt bridge, you allow the flow of ions to happen really neatly. It allows the ions within the solution to move. It allows there to be almost like a continuation of the circuit, and so it allows the electrochemical cell to happen better, stronger. No, not stronger, that's a bad word to use. More smoothly, I'll say. Prevents the buildup of charge at either electrode, there we go, which is going to push against the voltage, because charge of all ions in both half cells must remain at 0 to maintain electron flow. So you don't want to build up charge in one place by moving all the electrons into one place and not replacing them, or moving all the negative charge into one place and not replacing it, because then you're going to get a pushback, you're going to get electron-electron repulsion, and your current will not flow. So you'll get a resistance to the voltage. There we go. The most common salt bridge is a piece of what soaked in what? And by common salt bridge, we mean, in laboratories, in simple laboratories, the most common salt bridge is a piece of filter paper. So this is what you would be using, or what you would be describing you would use. A piece of filter paper soaked in what solution and why? It should be soaked in potassium nitrate. Why? Why have we chosen potassium nitrate? Of all the salts that we could have picked, why have we chosen potassium nitrate? You could be asked this. We do know it, or we should know it, in terms of our theory. It's because most potassium and nitrate salts are soluble. So the nitrate won't react with any of the metal salts to form a precipitate and take that metal salt out of solution, or that metal ion out of solution. And potassium also won't react or interact with most anions that are in solution, that are counteracting the metal ion in solution, to form a precipitate and to take it out of solution and to disrupt. Also, potassium is not going to, the potassium ion is unlikely to interact with the electrochemical cell either, because it is not easily reduced or oxidized. So potassium nitrate is used because it doesn't interact with the electrodes or with the electrochemical cell, and it doesn't produce precipitates, which will remove metal ions from solution. So it won't disrupt the cell by changing concentrations. I put conks because I'm being lazy, etc. Did I want to say anything else? Don't think so. Cool. So we won't have a go at doing this. Again, I can come back to it at the end if we have time. I'm just very aware that I'm doing a lot of talking today because there's a lot of theory to get through. So I just want to make sure that I get through as much of it as possible. Again, please feel free to have a go at it yourself. We will send around the answers once you've completed the feedback. La 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 la. Okay, so standard electrode potentials, and again, I'm going to reference them, make reference to them as being standard electrode reduction potentials because they are showing reduction. So a standard electrode reduction potential of a half cell is the voltage measured under standard conditions when connected to a standard hydrogen electrode, also known as an SHE. What are standard conditions? It's the same as we looked at yesterday. We just have the addition of a standard condition. There's a temperature, a pressure, and the addition is the concentration of ions. Temperature and pressure are the same. It's 298 Kelvin. Or if for some reason you want to remember it in degrees C and then convert it to Kelvin, not sure why you would, but if you do, 25 degrees C. So plus 273 to get it into Kelvin. Pressure is 100 kilopascals, so 100,000 pascals. And the concentration of ions in solutions must be, if it's a standard electrode, must be 1 mole per decimeter cubed. You may see it written down as 1 capital M, 1M. That means 1 molar, which is 1 mole per decimeter cubed. Lots and lots of old laboratories, not even old laboratories, lots and lots of laboratories use molar because they can't be bothered to say mole per decimeter cubed. It's the same. Molarity is the same. They're just being lazy. We have to be specific. So 1 mole per decimeter cubed. What else is going to say? Oh, yes. So the standard hydrogen electrode, when we are showing the measurement of the voltage of a half cell using the standard hydrogen electrode, like I keep saying, we put the standard hydrogen electrode on the left. This is where it's not always reduction on the right. Okay, this is the only time that I can think of off the top of my head where it's not reduction, not always reduction on the right. It might be, but it's not always. So we always put the standard hydrogen electrode on the left, no matter what which is being reduced or oxidized. You need to be able to describe what's necessary for the standard hydrogen electrode. So what's going on? What's happening? Because the standard hydrogen electrode uses the conversion of, or the conversion between H2 and H+ ions in solution, neither H2, which is gaseous, or H+ ions, which are aqueous in solution, are solid or can provide their own electrode. So what do we use instead as an electrode? That was a rubbish arrow. I'm going to do that again. What do we use instead as an electrode? We use platinum, a platinum electrode. Why? We use a platinum electrode because it's a good conductor of electricity, and it provides the surface for the reaction to happen on, for there to be an interface between the gas and the aqueous ions, and it's inert, so it doesn't react, it doesn't interact, it doesn't get in the way of our circuit. So platinum is our electrode. We need to have somewhere, can't seem to make this do what I want, there we go. We need to have somewhere to input the hydrogen gas. So usually we'll input it into almost like an upside down test tube, which will bubble the hydrogen gas over the electrode and allow the, the solution, which has got H+ ions in it, to interact with the H+. So start again. Allow the solution to accept H+ ions if necessary, and for the H2 to give up electrons, or vice versa. In some cases, obviously, it's going to go the other way around. No, it won't. Never mind. I'm being silly. You're just going to measure a different voltage. So what haven't I done? I haven't written H+ ions there. H+ aqueous. Haven't drawn the salt bridge. I'm going to write that there. Salt bridge. And obviously, this is a voltmeter. I'm going to label it, even though we don't need to label it. Is there anything else I wanted to say? Can't remember. Then the thing you are measuring against the standard hydrogen electrode will go on the right. I don't think there's anything else I wanted to say. No, okay. Let's keep going. What is the value of the standard hydrogen electrode and why? It is 0. Hopefully everyone got that. It is 0.00 if we're being specific, volts, because we set it as a reference. We have a couple of these in chemistry, one of them in NMR. So we set it as a reference, 0.00 volts. Hydrogen gas is bubbled into a H+ solution. This is what happens under standard conditions. Under standard conditions. And hydrogen is unreactive, so electrical contact is made through the unreactive metal coated in finely divided platinum. So we've got our platinum electrode. You can talk about it being a foil of platinum if you would like, or you can just call it a platinum electrode. You can also talk about a honeycomb shape. They like to use honeycomb shape. Do I mean shape? Structure. They like to use electrodes with a honeycomb structure because it provides a high surface area. Again, they're not that fussy. You can just call it a platinum electrode. It's fine. Coated in a finely divided platinum. Again, so this is where you could talk about it being honeycomb shape if you want. This is to increase the surface area. They may ask you about that. You don't need to name it as that unless they ask you. So to increase the surface area. Excuse me. Our hydrogen gas needs to be under standard pressure, so it needs to be at 100 kilopascals. Let's put my hydrogen gas in there. My solution is going to contain H+ ions. And it should be 1 mole per decimeter cubed, at least to begin with. What else haven't I done? Oh, electrode, platinum electrode. I can't think of anything else I need to write. I think that's it. So that's our standard hydrogen electrode, our SHE. SHE. Let's keep going. How are we doing for time? Okay. Right. So reduction electrode or electrode reduction potentials indicate how easily, this is where I don't like it, how easily a metal is oxidized. I think they show how easily a metal is reduced. The more negative an electrode potential it is, the more easily it's oxidized. That's correct. Personally, I think about it in terms of reduction, because that makes it easier for me to understand what's going on. So a zinc half cell is more negative, so it's going to be oxidized. A copper half cell is more positive, so it's reduced. Personally, I think about it in terms of reduction potentials. These are reduction potentials. So the more positive it is, the better at reduction it is. And that kind of fits together in my head quite nicely. So the more positive it is, the more likely it's going to do reduction, or the better at reduction it is, because it's more positive at reduction. Obviously, the vice versa is therefore true. The more negative it is, the more likely it's going to be oxidized. So for example, when we've got zinc and copper, the zinc half cell has a reduction potential of minus 0.76. So again, if I think about it as a reduction potential, it's minus 0.76. That tells me it doesn't want to be reduced, or its reduction is going to be unlikely to be reduced. The reduction potential of the copper half cell, so copper gaining 2 electrons in reduction to form copper solid, is positive 0.34. So that tells me that the copper is going to be going in the forwards direction, the reduction direction, and zinc is going to be going in the backwards direction, the oxidation direction. So this one is going to be reduction, and this one is going to be oxidation. I'm just being lazy with my denotions, writing red and oxen. Hopefully you know it means reduction and oxidation. What half equations would we write then? So I've kind of already gone through them, but let's just make sure we're happy. The half equations that show what is happening in a zinc and copper electrochemical cell are: copper is going to be reduced, so copper 2 plus electrons aqueous, sorry, copper 2 plus aqueous plus 2 electrons goes to make copper solid. And we're going to get zinc solid is oxidized to form zinc 2 plus aqueous and 2 electrons. So this is reduction, the top one, and the bottom one is oxidation. When I'm writing my half equations show oxidation and or reduction. So when I'm writing my half equations, I'm showing what is actually happening. I'm showing reduction happening and or oxidation happening. When you've got your electrode potentials, they are always written in terms of reduction. So there's often a little bit of a confusion there, but if it's written in terms of reduction, that means that doesn't always mean it will undergo reduction. It could undergo the backwards direction, it could undergo oxidation. So just bear that in mind, be careful with that. We also can consider writing them as full balanced equations. So to do that, we have to make sure that our exchange of electrons is equal. We can't have copper giving up 2 electrons and zinc only accepting 1 electron, for example, because then every time copper gives up 2 electrons, there's a spare electron floating around. Well, what's happening to that electron? So when you combine half equations, make sure you've got the same exchange of electrons, or you're exchanging the same number of electrons, in this case 2. So once I've balanced my electrons, I can combine my half equations and cancel anything that appears on both sides. So in this case, I have 2 electrons as both a reactant and a product, so I can cancel them. That means my full balanced ionic equation will look like this. Copper 2 plus aqueous plus zinc solid, I've cancelled my electrons, goes to make copper solid plus zinc 2 plus aqueous. Again, I have cancelled my electrons. That is the overall ionic equation. Hopefully everyone is okay with that at that point. Let's keep going. Because we can use our electrode or reduction potentials to calculate the standard cell potential. Now you can use this equation, if you would like, that is absolutely fine. But again, personally, I actually find this is confusing and would rather just think about or see if I can understand the theory and then use the theory. But if you can understand and use this properly, absolutely please use it because it makes it a little bit easier. But for me, that's another thing to remember, reduction minus oxidation, to remember it's that way around, and that it's reduction. So it's the reduction, nope, start again. It's the electrode potential for the half cell that is reduced minus the electrode potential for the half cell that is oxidized. That's actually what this equation means. So in both cases, I'm using the values that you're given in the equation, in the tables, sorry, even though in the tables, they're both shown for reduction. So when it says E cell oxidation, this is why I personally find it confusing. When it says E cell oxidation, we are giving the reduction potential for the cell that is oxidized. So you're doing reduction minus the reduction potential for the E cell that is oxidized, which is why it gets really confusing, okay? But if you've got your head around it and you're fine, carry on using it. If you're not happy with using the equation, I'm just going to explain it slightly differently, or just give you a different way to think about it, where you don't need to use an equation as such. You can work it out using what's going on. So this is also called the E cell potential, is also called the electromotive force. It's the push behind that cell. The bigger or the the bigger the difference between the reduction potentials, the more likely it is that a cell is going to happen, because one half cell is very good at reduction and the other one must be very good at oxidation. So you're going to get a very good flow of current. You're going to get very high EMF, electromotive force. That is the maximum potential difference between the two half cells. So the bigger the potential difference, the bigger the push of electrons, the better that is at being a cell, at behaving as a cell. So for the zinc/copper electrochemical cell, our E cell value, oopsies, is equal to, and I'm going to use the equation first to help us. So it's the reduction, the cell that is reduced. So reduction is the bottom one, oxidation is the top one. So copper is being reduced. So the value for my reduction, which is plus 34, minus the reduction value for the one that is oxidized. So minus 0.76. Minus a minus becomes a plus. So it's actually 0.34 plus 0.76. This is using the equation. This is probably how you learned it, and it's absolutely fine if this makes sense to you, then please carry on. Oh dear, let's try and make that look a bit nicer. That gives me a total of positive 1.1 volts. If it's positive, actually, let's just say that now. If it's positive, what does that mean for its feasibility? There's a positive EMF. It means that this reaction is feasible. It is possible. And which makes sense. If your copper is good at reduction and zinc is good at oxidation, well, then they can sit in a lovely circuit, oxidizing and reducing as they like. So this reaction is feasible. So that makes sense. The other way, just briefly, and please block your ears if you're happy with this and you don't want to be confused. The other way that you can think about it without having to memorize that equation is reduction is happening in the forwards direction. In the same way with exothermic and endothermic reactions, in one direction you get the positive value, in the other direction you get the negative value, but the enthalpy change is the same. It's just giving out energy in one direction, taking in that energy in the other direction. It's the same thing here. The forwards direction has a value of plus 0.34 for copper, but the backwards direction would have a value of negative 0.34. Similarly with zinc, the forwards direction has a value of minus 0.76. The backwards direction has a value of positive 0.76. So the way that I think about it is if I've got my copper going in the reduction direction and the zinc going in the oxidation direction, then I've got 0.34 in one direction and positive 0.76 for zinc. So I've got 0.34 plus 0.76 to give me my final push. That's the full push that's going around the circuit. That's how my brain works. And it's the same thing. All I'm doing by putting a minus in my equation is reminding me to flip the sign, basically, on the oxidation cell potential. So it's the same principle. Please do whatever suits you. I hate remembering things. I've got such a bad memory. So I have to try and understand what's going on. That's what's going on, is we're pushing the reduction cell we're pushing the half cell that is oxidized in the oxidation direction, which is the reverse direction. And so we reverse the sign and then add them together to get the whole number. Okay, let's keep going. How are we doing for time? What do I need? Okay, fine, I've got ages, good. Let's keep going, let's keep practicing. I'm just going to show that as therefore positive. So it's positive there. Okay, let's keep going. So there's also a shorthand convention for representing cells, and this confuses students a lot. I do get that. It's not covered in OCR. So you don't need to be able to write shorthand for electrochemical cells if you're in OCR. So you can have a very brief break. But for everybody else, there are two key rules. One, a vertical line indicates a phase boundary. Phase as in a difference between state or phase. So when you've got a solid electrode in an aqueous solution, for example, there is a phase boundary between those two, between the solid and the aqueous solution. Also, the double vertical line in the middle shows a salt bridge. Okay, so those are the two notations that we need to be aware of. That's where the double line in the middle shows where the salt bridge is happening. So it shows the division between oxidation and reduction. Now, point 3, again, this is where my theory slightly differs. The species with the most positive oxidation state is written next to the bridge. That is correct. Sometimes it's taught ROOR, ROR, but I find that really difficult because I have to remember that it's the species with the most positive oxidation state that's written in the middle. And so O, therefore, stands for the most oxidized. But in my head, it could stand for oxidation, as in the thing that's going to be oxidized. So I find it very, very difficult. So please feel free to remember it the way that you want to remember it. But the way that I have got my head around it is if you look at it and read it, as we do, from left to right, and we have written reduction on the right, as always. That's the other time. And oh no, I already said that, didn't I? Okay, never mind. Reduction is on the right. I know that there's at least 2 times where you write reduction on the right, and this is one of them. So I'm just going to write that up there. Let's write it in blue. Let's not be so angry in red. Reduction on the right again. So this is the reduction half cell on the right, that one. So on the right of the salt bridge. So that's my salt bridge in the middle. Salt bridge. So reduction is written on the right, the oxidation half cell is written on the left, and then you just read it like you do a book, like you do paper, from left to right. So that, if this has got to show oxidation, I have to show oxidation reading from left to right. And if this has got to show reduction, I have to show reduction reading from left to right. I know that it is actually technically other things to think about and other things to remember, but all I'm doing is reading from left to right. And I know that reduction goes on the right. So for me, I find that easier to remember than having to specifically put specific species in specific places, etc. And I know that this is oxidation because it's gone from a 0 oxidation state to a 2+ oxidation state. And the chloride has gone from a -1 oxidation state to a 0. So that must be, or it is, reduction. Okay. I think that's all I wanted to say. So OCR students, you can listen again. Shall we have a go? We won't have a go at this question because it's fairly easy and hopefully everyone can get it, but let's do this one. So it says, let's calculate the standard cell potential, the E cell value, using the values provided. So for the cell, we're assuming that there could be a cell happening between calcium and zinc. Calculate the standard electropotential for a feasible cell for this one. So what's my context? Standard cell potentials, I'm thinking electropotentials, fine. and feasible reactions. What's next? Command word. What's the command word? It's calculate. So I know I'm going to have to do some maths, some calculations, and I need to show my full working. Specifically, I've been given the values, so I need to calculate the cell potential using the values that I've been given. What are we thinking then? I'm going to give you less than 30 seconds while I take a drink. Okay. We didn't do part A. That was just giving the standard conditions. Don't forget that you need to give concentration as a standard condition for electrochemical cells because it's necessary for standards. Part B, calculate the standard cell potential using the values provided. What are we going to get to? So comparing the numbers, again, I work in terms of reduction because these are reduction potentials. It makes more sense to me. Feel free to do it oxidation if you would like, but the more positive of the two is going to be reduction because it's better at reduction. There's a reduction potential, so the more positive it is, the better it is at reduction, which in this case is actually going to be the bottom one. It's going to be zinc reduction, which means the top one, which is worse at reduction, therefore better at oxidation, must be the top one. So reduction is happening on the bottom. That means these technically should be reversible arrows. So the top equation is happening in the backwards direction, in the oxidation direction. Lovely. So this is more positive. That is reduction. Or if you would like to think about it in the other way, top one is more negative. We know that must be oxidation. So if you want to do it using the equation, it's the E cell for the cell that is reduced minus the E cell for the cell that is oxidized. So in this case, that would be minus 0.76 minus 2.87. Or we can skip that step and reverse the sign on the oxidation one and jump straight to minus 0.76, minus a minus is a plus, plus 2.87. I've reversed the sign in my head, so I can do minus 0.76 plus 2.87 to get me my final answer. I can't do that in my head. Positive 2.11 volts. You would get the same number either way, just make sure you're not reversing the sign twice. And I was going to say something else then as well. Always show your workings, especially if you aren't confident, because an examiner might be able to give you a mark for selecting the correct, for example, oxidation and reduction half cell. You might just lose the mark for maybe doing the calculation wrong. So always show your working, just in case you can gain a working mark. Okay, let's keep going. Oh, sorry. Oh, I didn't realize it was down there. Apologies. So, electrochemical series. They don't always just provide us with two half cells. Sometimes they provide us with loads. Sometimes they are put in order of increasing reducibility, of increasing reduction potential, so going from most negative to most positive. Sometimes they're not. Sometimes they're mixed up because they might be sorted for a different reason. They might be sorted, I don't know, in alphabetical order. They might be random. So just bear in mind, they're not always sorted from most least positive to most positive, but they are sometimes. This is in exam questions. But if we do sort them from most positive to, least positive to most positive, then we can see or we can discuss the trends that are happening with that. So as we've said, the more negative the E cell, the more easily oxidized something is. I actually think about it again in the reverse. The more positive the E cell, the more easily reduced they are. Again, we can link this back to stuff we looked at briefly earlier, which is oxidizing agents and reducing agents. I can't remember these. I can't memorize this, so I have to work it through. So the better at reduction something is, if it can be reduced very easily, Reduction is gain, so it can gain electrons very easily. That means it can steal electrons from things and cause something else to be oxidized. So the better at reduction something is, a half cell is, and I'm talking about the reactants here because that's the thing that is being reduced, the better at reduction it is, the more powerful the oxidizing agent it is because it's going to be causing things to lose electrons. On the reverse, the more negative something is, the worse at reduction it is, so the better at oxidation it is. That means it's going to be happening in the reverse direction because it's going to be, it itself is oxidized. So in that case, when we're looking at the top of the table, if they're put in order, we're looking at the species that is being oxidized as being the more powerful reducing agent because it needs to be oxidized to reduce something else. So in this case, it's the lithium, for example, that is going to be oxidized in the backwards direction to become lithium, a lithium ion. It's a really confusing and hard thing to get your head around, but I would highly recommend you spend a little bit of time working out, getting your head around making, you know, the oxidation versus reduction within these, within the electrochemical series. So up here, the equilibrium lies. I know they're shown as single arrows. They should be double-headed arrows, but here the equilibrium lies to the left. And down here, the equilibrium lies to the right. Have I done that the wrong way around? No, fine. The equilibrium, yeah. The equilibrium lies to the right, as in you're going to get lots of the forwards direction. Yep, there we go. You don't need to learn the E cell values. They will always be given to you either in the question or in your data booklet. So don't bother learning them. There's no point. How are we doing for time? Fine, let's have a go then. Using the table below, state which species is the strongest reducing agent given your reasoning. So let's think about how to approach this as an exam question. Context. Well, I'm talking about reducing agents and I can see the half cell. So my context is this must be electrochemical cells and electrochemical series. The command word I've been given is using. So use is a command word. State which species. So using data that I've been given, I need to give a short answer. And then my direction is the data that I've been given to use to come to a conclusion. So what are we going to say? I'll give it a second to have a think. So hopefully you've come up with an answer or you've got towards an answer. So which species is the strongest reducing agent? So the strongest reducing agent, I've got to think it through, otherwise my brain doesn't work. So the strongest reducing agent itself is going to be oxidized. So it's got to be the best thing at being oxidized. So which is the best thing at being oxidized? That will be the strongest reducing agent. So oxidized or oxidation is the reverse of the equations that are shown because it's got loss of electrons. So it's the reverse of these equations. So I'm looking at the thing as I go through the backwards reaction, the thing that is best at being oxidized. So worst at being reduced, that would be the most negative. And so in the backwards direction, that must be my calcium that can be oxidized to become calcium 2+. So calcium. Calcium is the strongest reducing agent as it has the most negative standard electric potential and so is more likely to be oxidized. Confusing. Hopefully you're happy with that. And we can move forwards to applications of electrochemical cells. Like I said before, there is a little bit of discrepancy between the exam boards. They also are not hugely clear on exactly how much detail they like you to give. So use your specifications as much as possible to make sure you're not learning more than you need, because there's more details out there than you need to learn, but also make sure you're covering the key points. Okay, so have a quick look. So for example, for Edexcel, you need to know both acidic and alkaline electrolytes. For OCR, recall of fuel cells and equations will not be required. So you need to be able to explain what a fuel cell does and how it works, but you don't need to be able to recall any equations. Great. For AQA, you need to do alkaline hydrogen oxygen fuel cells, but therefore they haven't mentioned anything about acidic. So the assumption therefore is you don't need to be able to do acidic. Okay, so it's very different across the exam board. So we're going to do a nice summary of what is most of the content that you share, but do bear in mind that there are discrepancies. So hydrogen oxygen fuel cells, one of the reasons this is in the specification is because it's an up and coming bit of theory. It's something that is important and useful in our use of fuels, as we hopefully all know, because we're running out of fossil fuels, and also they produce loads of pollutants. So when we burn them, when we combust them, so we don't really want to use them if we can. So coming up with a different fuel is really important. And hydrogen is an amazing fuel in terms of the amount of energy you can get out of it. But we don't want to burn hydrogen because that can be extremely explosive. It's also really difficult to carry hydrogen around the country. We'll come to that again in a minute. So we want to try and work out how we can use it. So fuel cells are an example. Fuel cells produce a voltage from reacting a fuel, which is usually hydrogen in a hydrogen oxygen fuel cell, but you can have other fuels in other fuel cells, such as methanol or ethanol, with an oxidant, something that can oxidize, i.e. oxygen. In hydrogen oxygen fuel cells, the fuel hydrogen is supplied continuously along with the oxidant oxygen, so the cell doesn't need to be recharged. I'm just going to highlight this as an advantage of fuel cells over what one would consider to be a normal cell, so a little replaceable battery cell, because if you have got enough fuel, you can continue to supply the fuel, then the battery or the cell, sorry, can go forever. In other cells, eventually you run out of metals in solution or the solid metal, and so the battery or the cell runs out of power, stops generating EMF, so stops generating a voltage. So one of the advantages of fuel cells is if you can continually supply the fuel, it can go forever, supposedly. Obviously, continuing to supply the fuel is easier said than done. But it means they don't need to be recharged. You don't have to recharge the cell to get it to work again. You can just keep going. Okay, both electrodes are coated in a porous, so honeycomb structure, or a film of platinum-based material, or what was the other phrase we used? A lattice structure. Again, for the same reason, to increase the surface area. Oops, to increase surface area. The electrolyte that we use can either be an acid or it can be an alkali. So you can either have an alkaline hydrogen oxygen fuel cell or acidic hydrogen oxygen fuel cell. But in both cases, the overall equation is the same. Yay! They both give the same overall cell reaction. So once we have taken into account both half cells, we've added them together and deleted anything that appears on both sides, we get the same half cell, which we're going to look at in a second. This is a diagram that shows an alkaline hydrogen oxygen fuel cell. We know it's alkaline because you can see the OH minus in the middle. So that's what makes it alkaline. That shows that it is alkaline. So I'm just going to pop that in there, alkaline. But let's consider what's happening then at the cathode and the anode, or at each electrode. On the left-hand side, we can hopefully see what is happening. we have got our OH minuses coming up and combining with the hydrogen H2 that is being input. It therefore is producing water, which we can then remove, and some electrons. The electrons can then pass through whatever it is we're trying to power, the battery, the motor, whatever, the voltmeter, if all we're doing is measuring it, onto the other electrode. And at that electrode, we then get oxygen incoming. It can accept electrons, mix with some water, which should be present as well, to produce OH minus ions, and the OH minus ions can then travel across. Now, this is often a semi-permeable, often a semi-permeable membrane, which allows the water to travel back and forth. Or you can also have water input as well, which we haven't shown here. So it does vary. Again, it depends which diagram you look at and which who's doing the explaining as to whether or not you have water input or whether it's come from the semi-permeable membrane or through the semi-permeable membrane. But we can tell that it is an alkaline fuel cell because of the presence of OH minus ions. Hopefully everyone's clear on that. The overall equation, you'll notice, if we combine one half cell and the other half cell, we come up with, and delete things that appear on both sides of the equation, we come up with 2H2 plus O2 goes to make 2 waters. That is our overall reaction equation. And it's possible for both, it's the same as I said for both acidic and alkaline conditions. What else was I going to say? Oh, yes. Which is oxidation, which is reduction? Hopefully you can tell using the half cell equations. There's also a phrase that you learnt at GCSE, which is applicable here if you wanted to use it, but you don't have to. I can see that here we are gaining electrons, so I know this has got to be reduction. Oil rig, reduction is gain. So this has got to be reduction. Notice again, it's on the right. And reduction is happening at the cathode. Reduction happens at the cathode. And oxidation, I can see this is oxidation because it's the loss of electrons. And this is also oxidation. And oxidation happens at the anode. Now, if you can remember, if you wanted to work it out, your cathode is the negatively charged electrode. It's negatively charged because cations, which are positively charged, are attracted to it. So a cathode must be negative to make sure they're attracted to it. And this is the one that's got the abundance of electrons. So this is going to be the negative electrode. Negative electrode. So if you want to work that out, you can therefore tell that that must be the cathode. And then this one must be the positive electrode because it is the one that is removing all of the electrons. So that must be the positive electrode. And the positive electrode is the anode because anions, which are negative, are going to be attracted to it. So you can work it out like that, or you can use the phrase which you probably learned at GCSE, which is an ox and a red cat. You may or may not have learnt it, but anyway, an ox and a red cat. So anode is oxidation, reduction is cathode. Personally, I'm not a massive fan of memorizing that because, again, you then also, as well as memorizing that, you also have to remember that it's talking about oxidation is happening at the anode and it's not talking about anions or anything like that, or, you know, an oxidized product or whatever. So personally, I'm not a massive fan. I'd rather work it out, but you feel free to use it to remember which one's which. If you're unsure in an exam and they haven't asked you to specify which is the cathode and which is the anode, you can just talk about one being positive and one being negative. If you're unsure, if you can work out which one's the positive electrode and which one's the negative electrode, then you can just discuss it as being a positive electrode and a negative electrode. You don't have to then define it as cathode or anode if you don't want to. unless they've explicitly asked for it. Okay, so in this case, I've already said that this is an alkaline oxygen fuel cell. And was there anything else I wanted to say? I don't think so, but I am just going to kind of make sure those are linked together. There we go. Okay, let's think about what have we've done alkaline. So let's think about acidic. So if you need to do acidic, it's here. So this is that. Sorry, that is where I need to put my line, because this is actually still alkaline. So that diagram is not applicable to this slide. So for acidic hydrogen oxygen fuel cells, I find acidic easier. I don't know why. I think because there's fewer water molecules getting in the way. But at the anode, H2 splits into H+ and an electron using the platinum catalyst. The proton exchange membrane, which is the bit in the middle, the semi-permeable membrane, which for alkaline allows the hydroxides across, but for acidic will allow protons across, H+. It forces electrode from the anode to the cathode, creating an electric current. That is where we get our cell happening. And then at the cathode, oxygen, O2, joins with the H+ that has traveled across the membrane and an electron to create water, to form water molecules, which is water is the waste product. Very nice waste product to have, actually, water. Okay, so unfortunately that diagram is not applicable here, but let's think about the equations, or look at the equations, because we've got them on the next slide. So as we've seen before, for an alkaline hydrogen oxygen fuel cell, at the negative electrode, that happens, at the positive electrode, that happens, and the overall cell reaction is the one that we've looked at before, 2H2 gaseous plus O2 gaseous goes to make 2 waters, liquid. And then for an acidic hydrogen oxygen fuel cell, as we said before, it's H2 splits into H+ and electrons, and then the H+ and the electrons join up with water on the other electrode to form, join up with oxygen on the other electrode to form water. But the overall cell reaction is the same for both. If you combine the two, cancel things that appear on both sides, then you can create the same overall cell reaction. Just note, we have specifically used 4 electrons in both cases, so we haven't necessarily got the simplest version. For the negative electrode, for example, for the both cases, if you were to write out the equation, you might choose to write it out with half the stoichiometric value. So 1H2 plus 2OH- goes to make 2 waters and 2 electrons, because that's the simplest balanced equation. We've written it doubled, so that you've got the 4 electrons, so you can see hopefully clearly that when you combine the 2 equations, you can cancel all 4 electrons, the 4 electrons on both sides to come up with the same overall cell reaction for both. But just as a note, you might see it written differently in the half amounts. Same with the negative electrode for the acidic hydrogen oxygen fuel cell. You might see it written as H2 goes to make 2H+ and 2 electrons, because that's the simplest way of writing the balanced equation. It's the same, all we've done is doubled it, just to make it easier to see that you can cancel the electrons to create the overall cell reaction. Both would be given, multiples of equations are given, unless, as I mentioned loads before with Born-Haber cycles, unless it's explaining a specific process which requires specific molarities. In this case, it doesn't. We're just looking at the ratios. So you could write an equation that shows a multiple, and you would be correct. So if you want to memorize it and memorize it in multiples, that's fine. So both acidic and alkaline conditions give the same overall cell reaction. So that makes it a little bit easier. Okay, let's keep going. We're doing quite well for time, which is nice, I think. Yes, let's keep going. So let's think about our advantages and disadvantages. I have kind of mentioned some of these already before, which is quite nice. But let's just confirm them. So they, not always, they do ask for equations. They do ask for, oxidation and reduction equations and combining them to make the whole cell. But a lot of the time, what they ask about when we talk about hydrogen oxygen fuel cells, because there's such variety out there, is the advantages and disadvantages, because they stay the same no matter what your hydrogen oxygen fuel cell looks like. So advantages to hydrogen oxygen fuel cells or fuel cells in general, you can apply some of these to fuel cells in general. They're a greener alternative to fossil fuels. So methanol or biofuels you can use in fuel cells are greener alternatives. There are no pollutants formed with a hydrogen oxygen fuel cell because the only waste product, oh, I nearly dropped my mic, let's put that back. The only waste product formed is water. So that makes it a bit nice. Hydrogen oxygen fuel cells are much more efficient, for example, than combustion engines, because combustion engines, there's a huge amount of heat energy wasted. As engines get ridiculously hot. That's energy that you want to be converting into kinetic energy that's being converted into heat energy. So they're not very efficient. So hydrogen oxygen fuel cells are much more efficient. They're not 100% efficient. They're never going to be, because we've still got friction and gravity and all these things to contend with. But they are more efficient, which is good. Disadvantages, though, and they're quite big disadvantages. Hydrogen is a gas and at room temperature and pressure, and it is explosive. It combusts very quickly. It will go up very quickly. Therefore, storage of hydrogen within your fuel cell and the transport of hydrogen across the country, if we wanted to use hydrogen oxygen fuel cells, for example, to power cars, you'd have to transport hydrogen gas across the country. That is going to be really hard to do. It's going to be expensive. It's going to be potentially dangerous. And we're going to need to put an infrastructure in to transport hydrogen gas across the country. At least when we've got our combustion engines, we're using fossil fuels. Fossil fuels like diesel and petrol can be carried around in tankers, which can be driven up and down the country. We've got infrastructure for that. We don't have infrastructure for moving large tanks of hydrogen gas around. So that needs to be considered. Also, unfortunately, lots of the cells, you might even have recognized it in terms of cells with your phones and other technological things. The production of those cells involves toxic chemicals, which need to therefore be disposed of carefully. There's also the use of all these raw materials, but that's kind of the same with everything. But hydrogen oxygen fuel cells, the platinum catalysts, for example, and the membranes can be made of resources of which we don't actually have that many of anyway. So although hydrogen and oxygen are abundant within our Earth and the atmosphere, the other chemicals are A, toxic, but B, a lot more scarce and a lot less available. So not so useful. That's a disadvantage. Okay, how are we doing for time? 5 minutes. Yay, let's have a go at a question. So have a go at this question and then I will go through it in a second. I'll give you less than a minute, 30 seconds or so to have a go. So with this question, it's asking, in an alkaline hydrogen oxygen fuel cell, the half equations involved are blah, 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 and blah, blah, blah. Oh. I think there's an error there. I don't know if this is the same as what you've got in front of you, but there's an error there. So let me just correct that. It should say, let's do 2, 4, 4, 4. And then that should be 2O2 plus, no, it shouldn't. It should be just O2 plus 2H2O plus 4 electrons goes to make our hydroxide, 4 hydroxide. It looks like someone's written the acidic, no, in fact, I don't know what they've done, combined half the acidic and half the alkaline fuel cell equation. So apologies for that. It shouldn't say that. It should say 2H2 plus 4OH minus goes to make 4H2O plus 4 electrons, and O2 plus 2H2O goes plus 4 electrons goes to make 4OH minus. So the question is still explain how electric current can be generated. In my brain context, I'm thinking hydrogen oxygen fuel cells, so electrochemical cells, specifically hydrogen oxygen fuel cells. The command word is explain. So they're looking for a wordy answer. They're looking for an explanation about where we get electric current from. Electric current is the flow of electrons. So they're looking for where we get the flow of electrons or how that comes about. And specifically within an alkaline hydrogen oxygen fuel cell using the equations that we've been given. So 2 moles of hydrogen split and release 4 electrons. See, this is correct, isn't it? Yeah. Whoops. I don't know if you've got this slide in front of you. Apologies if you don't. Hopefully you've corrected the previous one. If not, maybe just make a quick note to double check when you get the answers later. So an answer you could give would be 2 moles of hydrogen splits and releases 4 electrons. Electrons flow to the positive electrode where they are accepted by oxygen, which combines with water to form OH minus ions. This flow of electrons generates electric current. Something along those lines. How are we doing for time? Oh my gosh, we're actually early. Whoa. That's amazing. Okay, apologies for that though. I will make a note that that is wrong so that that can be corrected. Lovely. Okay. We are actually 2 minutes early, so that's exciting. So let's have a slightly longer break. We're going to have a break until 3:15. So that's just 7. No, we're not. Sorry, we've passed 3:15 till 3:45, 15:45. It's because I saw the 15. 3:45. So 17 minutes or 16 probably by the time I finish talking. During this break, I'm going to put up. Am I the right one? Yes. During this break, I'm going to put up a link to the survey that you need to fill out. If I can get it up, if I can find it. If you can copy it down so that you can look at it later, or if you can go on to it during the break and fill out the survey, that's absolutely fine. Or if you'd like to wait until the end, so until we've had our final session, which is organic synthesis, then please feel free to do that. I will put the slide up again at the end so that you will be able to fill out the form, the feedback form at the end, and therefore you can make sure you can input your email address to get the answers sent over, etc. So, you see, 16 minutes. Have a lovely break. I'll see you in 16 minutes. We'll come back at 1:45, where we'll finish up with some organic synthesis. Thank you very much.